Okay, well, thank you so much. It's a great pleasure to be here this term, and in particular for this workshop. I'm very grateful to the organizers for putting this wonderful semester together and this workshop, and inviting me to give too many talks. Okay, so there are 2 points that I sort of want to make in these talks. Maybe I'll try to get out of the last one. I think it was too many, actually. Well, let's see. Okay, we'll see. But the 2 points I want to make in these talks is, first, in describing the distribution of arithmetic objects, which is sort of the goal of this workshop in this semester, it's often helpful to know how to explicitly write down these objects, and how, in particular, how to explicitly parameterize arithmetic objects. And so that's sort of the theme for the lecture today, some background today and then tomorrow. And what I want to argue is that one good way to parameterize algebraic objects is through orbits of representations of algebraic groups. So that's going to be an example of a kind of parameterization that is useful in studying distributions of arithmetic objects. And I want to give about, I'll probably give about 100 such examples in these lectures. It's not a very well understood theory. There are lots of examples now, but it's more of an art on how to produce such parameterizations of algebraic objects. And so that's kind of what I want to build up to in these first 2 lectures. And then the second point I want to make is that once one has such a parameterization of algebraic objects, then to try to understand the distribution, the statistics of these objects, one has to develop methods of counting these orbits. Say, if we're parameterizing by orbits of group representations, we need a way of counting these orbits. And so various ways can be developed to do that. One is geometry of numbers. That's what I'll mainly be talking about, but there are other methods as well. For example, zeta function methods, as Frank will talk about, Frank Thorne will talk about at the end of the week. Okay, so those are sort of the 2 main themes of these lectures. So let me talk about one such parameterization that goes back. So this is sort of background. I apologize if you've seen these things before, but this is sort of where I personally got started. But this is from the Disquisitiones of Gauss, an example of an algebraic group representation that he studied in his Disquisitiones is the binary quadratic form. So binary quadratic form is a lattice. The set of all binary quadratic forms over the integers form a lattice in a 2-dimensional representation of SL2. Okay, so binary quadratic form for our purposes will be anything of the form ax squared plus bxy plus y squared, where a, b, and c are integers. And so Gauss studied these set of integral binary quadratic forms. Actually, Gauss always assumed b is even, but that we'll ignore that for now. And if you look at binary quadratic forms, there's a natural action of SL2z on the set of integral binary quadratic forms by linear substitution of variable. You can replace x by a linear combination of x and y by a linear combination of x and y, and that sends an integral binary quadratic form to an integral binary quadratic form if your matrix of substitution was integral. And if it has determinant 1, so if you're in SL2z and you're doing a linear change of variable that has determinant 1 over the integers, then it'll send integral binary quadratic forms to integral binary quadratic forms. And moreover, something will be preserved, namely this expression that we all know, b squared minus 4ac. So b squared minus 4ac is something that remains unchanged under the action of SL2z on integral binary quadratic forms. And in fact, it's the unique invariant for this action, in the sense that if you look at the ring of polynomial invariants, so all polynomials in A, B, and C that stay the same when you do SL2z changes of variable, then any such polynomial that remains invariant will be a polynomial in b squared minus 4ac. Okay, so in that sense, it's the unique polynomial invariant. Okay, it generates the ring of invariants for this action. Okay, so this is a natural representation of the group SL2z on a lattice, namely this 3-dimensional space of binary quadratic forms. Okay. And so we can ask, what do the orbits parameterize? Okay, what do the orbits of this action mean? So if you look at, so the discriminant is preserved. So if you look at all binary quadratic forms that have a fixed discriminant, it's a theorem of Minkowski that says that the number of such orbits is finite. And so we can ask how many such orbits are there, for example. So what Gauss proved about these orbits was a certain group structure. So what he said is that if you take the set of SL2z equivalence classes of primitive integral binary quadratic forms of a given discriminant. Okay. So there are only finitely many such things. So if you look at a number that's 0, 1 mod 4, call that D, and you look at all binary quadratic forms that have that discriminant, that value of b squared minus 4ac, up to this SL2Z equivalence, then that set of primitive integral binary quadratic forms has a group structure. And it's what's nowadays called the narrow class group of the unique quadratic order that has that discriminant D. So this is called Gauss composition. So what Gauss is saying is that the set of orbits that have a given discriminant, set of integral binary quadratic forms that have a given discriminant up to SL2Z equivalence, they naturally form the structure of a group, which is nowadays called the narrow class group. So this was quite a discovery because the notion of group hadn't existed yet. So in modern language, this group that's in theorem 1 is called the narrow class group of the unique quadratic order that has that discriminant, D. So unique order in a quadratic field. That's the discriminant of order is D. If you look at the narrow class group of that, that's exactly the group that's being parametrized by the orbits of this group action. So this is the first example sort of a parametrization of an arithmetic object, namely the narrow class group elements of quadratic orders, by the integer orbits of a certain group action of an algebraic group, namely SL2. And so I'd like to say this is still one of the best ways for enumerating class group elements of quadratic fields. And so this is something that struck me when I was a graduate student, is that you can parameterize this arithmetic object, namely class group elements, by the integer orbits of a group representation. But I was struck by the fact that this is something that's been used so much, and yet it only applies to, for example, to quadratic fields, to orders in quadratic fields. So the question was, do there exist other, I was looking for, in particular for group structures, but one can ask even more generally, are there other spaces of forms besides binary quadratic forms or other representations of algebraic groups that might have similar structures to what Gauss discovered for binary quadratic forms? So for example, could one use other spaces of forms to shed light on higher degree number fields, okay, instead of quadratic number fields? So it's still a very vague question. I'm going to try to make it a little more precise. So I'm going to phrase this as an orbit problem. Okay. So Gauss composition can be stated in modern language as the solution to an orbit problem. So by an orbit problem, I just mean you have a group, you have a representation. What do the orbits mean? Okay, what do they parameterize? And the way you can think of Gauss composition is as follows. You can think of, so Sim2Z2 is just a notation for binary quadratic forms. It's the symmetric square of the standard representation of SL2. If you look at the space of binary quadratic forms, modulo the action of SL2Z, then what Gauss is saying is that these orbits are in one-to-one correspondence with pairs S comma I, where S is an order in a quadratic field and I is an ideal class, a narrow ideal class in that quadratic field, in that quadratic ring, quadratic order. Right, so that's a way of thinking about Gauss composition, and what his composition law was just multiplying ideal classes on the right. Right, and that leads to a group structure on the objects on the left, namely the orbits for the action of SL2Z on binary quadratic forms. Okay, so Gauss composition is really a solution to an orbit problem for a particular algebraic group over the integers acting on a lattice in a representation of that group. So in general, we could consider any algebraic group G and any so defined over the rational numbers or over the integers, and any rational representation V of that algebraic group. And we want both of these to have be defined over the integers so that we can talk about the lattice of integer points in V being acted on by sort of by the integer elements of G. And we can ask the same question that Gauss solved for binary quadratic forms in SL2. We can ask for what pairs G comma V, where G is an algebraic group and V is a vector space, okay, both defined over Z. What does the action, what do the orbits of the action of G of Z on V of Z mean? Okay, in terms of, say, rings or modules. what algebraic objects are parametrized by the integer orbits of a general group representation. So for example, when V was the space of binary quadratic forms and G was SL2Z, then what we were parametrizing was ideal classes in quadratic orders. Okay, so Gauss composition gives one solution to a particular case of V and G. Okay, well, it's still a pretty vague question. And the main question that arises first is, well, where do you look for more such representations? Okay, so first of all, what's special about the space of binary quadratic forms that allowed one to get a parameterization of orders and number fields and class group elements? Okay, what was special about that representation? Okay, well, one key observation that you can make about binary quadratic forms is that if you look at the action of GL2, say GL2C, over binary quadratic forms over C, then that action has essentially just one orbit. It has one Zariski open orbit. So if you look at the action of GL2 on the C, on the space of binary quadratic forms over C, okay, then that has just one Zariski open orbit, namely those binary quadratic forms that have non-zero discriminant. Right? The way you can sort of see that is a binary quadratic form cuts out 2 points in P1, and any 2 points in P1 are equivalent to any other 2 points in P1 by a linear fractional transformation. And that exactly is the transformation in GL2 that will take the binary quadratic form that has those two roots to the binary quadratic form that has the other two roots. Okay, so there's essentially just one orbit, one Zariski open orbit for this action. So that's something special about the representation of binary quadratic forms. And in general, so Henri already mentioned this morning, so in general, a representation like that, a pair G comma V, okay, so a G algebraic group V, a representation, such that there's just one Zariski open orbit over the complex numbers. That's called a prehomogeneous vector space. So that representation is called a prehomogeneous vector space if there's just one Zariski open orbit for the action. So binary quadratic forms is one example of a prehomogeneous vector space, and we can ask, are there other such representations? That may be a first place to look for other parameterization spaces, such as Gauss's. So are there other such representations? And the answer is yes. And Sato and Kimura gave, in 1977, they gave a classification of all prehomogeneous vector spaces because there are certain applications in representation theory of such spaces. We're looking for applications in arithmetic, but luckily they came up in another subject beforehand. And so what Sato and Kimura proved is that there are 36 of them. There's 36 such representations. This is under certain conditions. So they're assuming certain niceness conditions, namely that the representations are irreducible, that G is a reductive group, and there's another technical assumption that, another niceness assumption on the representation. So if you assume certain niceness assumptions on what G and V satisfy, for example, that they're irreducible and so on, then you find that there are only 36 such representations in the world. That's kind of a lie because some of these are infinite families. Okay, so that's something good. Okay, so we can look at these representations. This is a good place to start. Binary quadratic forms is one of the first ones that appears on this list. And then you have all these other representations that go on from there. And you can ask, what do the orbits over the integers look like? Okay, just like for binary quadratic forms, the orbits over the integers are really interesting. They parameterize ideal classes in quadratic fields, in quadratic orders, even though over the complex numbers, this is a completely boring representation. It only has one orbit. Right? But over the integers, suddenly all this rich arithmetic comes out. And the same question can be asked for other representations that for people who just study over the complex numbers, these are totally boring representations because they only have one orbit. But if you look over the integers, then there's a possibility that a rich arithmetic structure will emerge. So before looking over the integers, maybe you want to look over a field other than the complex numbers. Okay. And if you look over fields other than the complex numbers, for example, over the rational numbers, then this was studied by Wright and Yuki in 1990. And they showed that orbits of several of these prehomogeneous vector spaces over, say, the rational numbers, those orbits corresponded to field extensions of the base field. So over Q, the orbits corresponded to field extensions of Q of a given degree, the degree being 2, 3, 4, or 5. or 1 sometimes. Yeah? No, they don't. Yes, that's a good point. So they found models over Q, such that if you looked at the orbits over Q with that model, then this is what they corresponded to. That's a very good question. So actually, they're just 36 over them over the complex numbers, but now if you start looking at models over Q and over Z, there are actually lots and lots of forms. And sometimes those different forms parameterize different things arithmetically. And that's actually very useful. Very good question. Okay, so what Wright and UK's result already shows is that there is some arithmetic going on in these prehomogeneous vector spaces, because if you look over Q, you're getting field extensions. So already there is some arithmetic going on. And so when I saw this, I thought, okay, well, the goal should be, we should understand, not just over the rationals, we should understand integer orbits. If we look at an integral model of one of these representations, and we want to understand VZ mod GZ for prehomogeneous vector spaces G comma V. Okay, will they have? So a lot of rich arithmetic structure should come out. So for example, one way you could have guessed that binary quadratic forms would be interesting integrally is that if you look first over the rational numbers, binary quadratic forms over the rational numbers parameterize quadratic fields. Namely, you look at the two roots and see what field they're defined over. Right? So you already see quadratic fields in binary quadratic forms just by looking over the rational numbers. And then when you go to the integers, you start seeing ideal classes coming out. So that richer arithmetic information. So same thing, we can ask for other prehomogeneous vector spaces, do the integral orbits correspond to even richer arithmetic objects than just number fields? So there's one other piece of data beyond Gauss composition, beyond binary quadratic forms, namely binary cubic forms. So this piece of data was already there before I even thought about this question. So what about binary cubic forms? Okay, we know binary quadratic forms parameterize ideal classes in orders in quadratic fields. What happens with binary cubic forms? So I learned about what binary cubic forms parameterize over the integers from a paper of Wietek, Gan, and Gross and Savin. And what they showed is a refinement of a classical result of Delaunay and Faddeev, which states the following. It says that if you look at the GL2Z orbits on integral binary cubic forms, the GL2 and the SL2Z don't matter too much. There's only one is index 2 in the other, so it's not a big deal. So they look at the GL2Z orbits on integral binary cubic forms. They're in canonical bijection with cubic rings. So what is a cubic ring? A cubic ring just means a rank 3 free Z module that has a ring structure. It's like a Z3 with a ring structure. So your prototypical cubic ring is an order in a cubic field. So what this result is saying is that if you take the GL2Z orbits on integral binary cubic forms, okay, they're in canonical bijection with orders in cubic fields, basically. Okay. So it's kind of similar to the binary quadratic case, except the ideal class disappeared. Right? So in the binary quadratic case, you had a quadratic ring plus an ideal class. Here, you lose the ideal class, but you do parameterize cubic rings, which is a very non-trivial object compared to quadratic rings, for example, which are very easy to parameterize. Quadratic rings are basically determined by their discriminant. Okay? An order in a quadratic field will be determined by what its discriminant is. An order in a cubic field, there can be many orders that have the same discriminant. So you need finer information to parameterize orders in cubic fields. And that finer information is integral binary cubic forms. Those completely, the orbits of binary cubic forms completely parameterize cubic rings. And here's how it works. It's very pretty. You can make it very explicit. If you have a binary cubic form, ax cubed plus bx squared y plus cxy squared plus dy cubed, where a, b, c, d are integers, then here's how you can make a cubic ring. Okay, so you say the basis of your cubic ring is going to be 1 omega and theta. So how do you specify the ring structure on a lattice parameter having basis 1 omega and theta? You basically have to specify what omega squared is, what theta squared is, and what omega times theta is, because we know what 1 times anything is. Okay. So using ABCD, we want to specify a ring structure, and so we just have to define what omega theta is, define to be minus AD, what omega squared is, take that thing, take what theta squared is. And so using the coefficients of the binary cubic form, we made a cubic ring. So these are formulas of Delaunay and Faddeev. And you check that this actually defines a ring structure. You check associativity, and it's clearly commutative, and so on. But it's associative. That's the miracle. And so that gives a cubic ring. And conversely, if you have a cubic ring, then you can write the multiplication table in this form, always, you show. And then that gives you a binary cubic form, A, B, C, D. And if you do a GL2Z change of basis on the cubic ring, then what you find is that the binary cubic form also changes by that action of that same element of GL2Z. So if you change the basis omega theta to some GL2Z change of basis of omega and theta, then that'll act then that same way on the binary cubic form. So that's why you get a bijection, a natural bijection between GL2Z orbits on binary cubic forms and orders in cubic fields, basically cubic rings. If this is too explicit for you, a basis-free way to get to a binary cubic form from a cubic ring, well, if you're given a cubic ring R, if you look at what's called the index form, 1 wedge x squared, that's a cubic form that takes values in wedge 3 of R, which is one-dimensional, so it's basically Z. So it's basically a binary cubic form on R mod Z. So R mod Z is two-dimensional. It's a cubic form. So that gives your basis-free way of constructing a binary cubic form. OK, so this is a solution to another orbit problem. It says that binary cubic forms parameterize orders in cubic fields. And as I'll talk about later, this indeed is the parameterization behind all the Davenport-Heilbronn theorems and all the later works in that direction. So parameterizing algebraic objects in terms of orbits of group representations, that's already was behind this work of Davenport and Heilbronn. OK, so our question is, well, how do we come up with more of these? We have binary quadratic forms. We have binary cubic forms. OK, why not go to binary quartic forms next? Well, binary quartic forms are not pre-homogeneous, because if you take 4 points in P1, they're not equivalent to any other 4 points in P1. So there's not just so binary quartic forms are not pre-homogeneous. So that's not the next place to go. So if you look at the list, you can look at the list of all pre-homogeneous vector spaces on Sato and Kimura's list, and you find, well, of course, binary quartic forms are not there. Many other things are there. And how does one go into one of them and start analyzing the integer orbits? It's something, well, it's kind of daunting, because some of these spaces are 40, 50 dimensional. They're very big. And so to try and just analyze the integer orbits in one of these representations is a very daunting thing. Even if you look at the original treatment by Gauss of binary quadratic forms, that already takes like 20 pages of computations to prove that there's this group structure and this correspondence. So the way I thought to start was to look at Gauss composition again and try to come up with a way that might incorporate other spaces into Gauss's original Gauss composition, and then see how that could maybe generalize. So here was the idea. What would happen if we put numbers on the corners of a cube? So it's a 2 by 2 by 2 matrix. So when one has a 2 by 2 by 2 matrix, then one can slice. Okay, so this is a 2 by 2 by 2 matrix. Let's consider A, B, C, D, E, F, G, H to be integers. And what would happen if you slice the cube into pairs of 2 by 2 matrices? So if you have a 2 by 2 by 2 matrix, you can slice the cube on any of the 3 planes of symmetry to get two 2 by 2 matrices. Right? So for example, if you cut off the front face from the back face, you get A, B, C, D, and then E, F, G, H. Right? Or if you take the left face and the right face, you get these two matrices. Or if you take the top face and the bottom face, you get these two matrices. Okay, so anytime you have a 2 by 2 by 2 matrix, a three-dimensional matrix, 2 by 2 by 2, you can slice it into two 2 by 2 matrices in essentially 3 different ways. Okay, so what do you do when you have two 2 by 2 matrices? There's a natural thing to do if you're presented with a pair of 2 by 2 matrices. which is you can take the family of matrices, the linear span, the linear family of matrices that go through M1 and N1, say, and take the determinant function, okay, because you can take a determinant of a 2 by 2 matrix. So in other words, you can take the determinant of M1x plus N1y, where x and y are indeterminates. Right? And since the determinant is degree 2 on 2 by 2 matrices, this is a binary quadratic form. Right? I put minuses there, but they're not so important. In the same way, if you have another pair of 2 by 2 matrices, we have 3 pairs of 2 by 2 matrices. And on each one, you can take x times the first plus y times the second and take the determinant. And that'll give you a binary quadratic form. And so what that means is that anytime you have a 2 by 2 by 2 matrix, it spits out 3 binary quadratic forms. So the situation is similar, and there'll be an explicit correspondence with elliptic curves that I'll talk about later in the week. But just like when you have a plane elliptic curve, and you take a line in the projective plane, it'll intersect the cubic curve in 3 points. And one way of defining the elliptic curve law on elliptic curves is to say the sum of those 3 points is 0. And so this is something analogous. Here we have a 2 by 2 cube, and it spits out 3 binary quadratic forms. So a natural way to try to define a group law in binary quadratic forms is to say, let's say the sum of those 3 things is 0. So one checks that if you look at the discriminant of each one of these 3 binary quadratic forms, you can just write out the discriminants are the same of all 3 of these binary quadratic forms. And so if you take sort of the freewheeling group generated by all binary quadratic forms of a given discriminant, modulo all such relations that come from cubes. So if you say that for every 2 by 2 by 2 cube, the sum of the 3 binary quadratic forms that it spits out is 0. That defines that punchline is that agrees with Gauss composition. So for every 2 by 2 by 2 cube, you get 3 binary quadratic forms, and the sum of them is 0 under Gauss's group law. So this gives at least a very short way of describing what Gauss composition is in terms of 2 by 2 by 2 matrices. And the process that went into making this definition is sort of an unfolding process. We took binary quadratic forms and we unfolded them into these sort of 2-2-2 trilinear forms, right? So we took quadratic forms and made them multilinear. That's sort of what's going on here, and that's a theme that will occur throughout these lectures. You can take complicated objects and that look like they have high degree and make them multilinear instead by this kind of unfolding process. And then a lot of the things that seem complicated for the high degree forms become simpler when you think of them as multilinear forms. Okay, so this is a way to think of Gauss composition. Notice that the action of GL2Z is automatically incorporated in this. So you can think of the spaces of 2 by 2 by 2 matrices as Z2 tensor Z2 tensor Z2, which is a representation of SL2Z cross SL2Z cross SL2Z. Right? And so SL2Z, the first SL2Z acts by row operations, and the second SL2Z acts by column operations, and the third SL2Z acts in the other directional operations. Right? And if you look at these formulas for how you define the binary quadratic forms, if you use the first SL2Z, it's going to change basis on this quadratic form, but keep these two the same. And so if the sum of those 3 is 0, and the sum of those 3 is 0 even after you do an SL2Z change of variable, what that means is that a binary quadratic form and its SL2Z equivalent are equal in the group, because you're modding out by both those relations. So the SL2Z action is sort of automatic in this. You don't have to explicitly say it. It comes automatically. Okay, so how does this contain? So this is a description of Gauss composition. And so what I want to point out now is that not only does this give a description of Gauss composition, but it in fact gives composition laws on other prehomogeneous vector spaces, not just binary quadratic forms. For example, the space of cubes themselves. If you look at the space of all 2 by 2 by 2 matrices, that's a prehomogeneous vector space under the action of SL2Z cross SL2Z cross SL2Z. So Z2 tensor Z2 tensor Z2, that's space of 2 by 2 by 2 cubes, if you mod out by the action of SL2z cubed, in other words, the action of row operations, column operations, and the other directional operations, right, then those orbits, what that discussion is saying is that those orbits are in one-to-one correspondence with a quadratic order, S, and 3 ideal classes, namely the ideal classes corresponding to those 3 binary quadratic forms that the cube spits out. Okay. So another way of thinking of this operation I said there is as the solution to an orbit problem, namely the cubes, space of cubes, modulo SL2z cubed, is in one-to-one correspondence with this is the object being parameterized, quadratic order together with 3 ideal classes that sum to 0 in the class group. And so that gives, just like the binary quadratic form discussion gives a composition law in binary quadratic forms, this discussion gives, okay, so the way to think of Gauss composition is that you can multiply ideal classes, right? So this corresponds to a binary quadratic form of a given discriminant. This is a binary quadratic form of the same discriminant. You can compose them by just multiplying the ideal classes. That's what Gauss composition means in terms of ideal classes. Gauss described it in terms of the forms. But in the same way, we have now a composition of cubes, right? Because if you have a 2 by 2 by 2 cube, that corresponds to 3 ideal classes that sum to 0. And if you have another cube, that you have 3 more ideal classes that sum to 0. And you can multiply them by just multiplying those 3 ideal classes that correspond to each other. Right? And one can actually describe this purely in terms of the cubes. You have a 2 by 2 by 2 cube and another 2 by 2 by 2 cube of the same discriminant. Then you can give an algebraic formula that produce a cube here. But in terms of ideal classes, in terms of what those orbits parameterize, this makes it very clear what the composition should mean. It corresponds to multiplication of the respective ideal classes. Okay, so what we're saying is that not only do binary quadratic forms have composition, but 2 by 2 by 2 cubes also have composition. And this has an interesting consequence in that, so the number of orbits of a given discriminant for binary quadratic forms is the narrow class number, right, of the quadratic order. In this case, it's the narrow class number squared, right, because I1 and I2 can be anything, and then I3 is determined by the fact that the sum of these 3, the product of these 3 is the trivial ideal class. So a consequence of this is that the number of orbits of cubes having a given discriminant is always a square. Which is something that wouldn't be easy to see without this, I think. Okay, so what I want to say next is that, okay, so composition of cubes, you can compose cubes, you can compose binary quadratic forms, and I want to point out that the same composition law allows one also to compose not just binary quadratic forms, but binary cubic forms can now be composed. And the reason is that, well, you can impose symmetry. So if you look at just the space of triply symmetric cubes, right? So if you hold a cube on the diagonal and you start rotating, right, then there's an order 3 symmetry there. So let's look at all cubes, 2 by 2 cubes, 2 by 2 by 2 cubes that stay fixed under that rotational symmetry of order 3. Yeah? So it looks like that, right? So you have A and D as the diagonal. And now if you rotate along the diagonal through A and D, the B's go into the B's and the C's go into the C's. Right? So this is a triply symmetric cube. And so what do triply symmetric cubes mean? Well, what do symmetric squares mean? If you have a symmetric square matrix, you can think of that as a quadratic form. Right? So in the same way, if you have a triply symmetric cube, you can think of that as a cubic form. So if you have a triply symmetric cube like that, you can think of it as right, it's a totally symmetric trilinear form, so you can think of it as a cubic form, or a symmetric trilinear form. So you can identify it with the cubic form ax cubed plus 3bx squared y plus 3cxy squared plus dy cubed. So triply symmetric cube you can think of as a binary cubic form, except that there are these 3's in the middle. In terms of representation theory, what's going on here, if you have a cube, which is Z2 tensor Z2 tensor Z2, and you look at a totally symmetric version of that, that's sim3 of Z2, right? So the symmetrization process takes space of cubes to space of binary cubic forms. And now we can specialize what we said for cubes. We know what cubes parameterize, and so what do triply symmetric cubes parameterize? Well, what did cubes parameterize? Cubes parameterized an order in a quadratic field together with 3 ideal classes that multiply to the trivial class. If the cube is totally symmetric, that means those 3 ideal classes are all the same. Right? And they multiply to the identity. So what that means is that you're isolating a 3 torsion element in the class group. Right? Because you have 3 ideal classes that are all the same and they multiply to the identity. So this gives a solution to another orbit problem. Namely, if you take the space of binary cubic forms with 3's in the middle here, that's kind of key, modulo the action of SL2Z, then these orbits are in one-to-one correspondence with an order in a quadratic field together with an order 3 ideal class, a 3 torsion ideal class. So this method has extracted a particular type of torsion in the class group of the quadratic field, or of the quadratic order. And this really is sort of what's behind when Henri talked about the special cases of Cohen-Leinster that were proven by Davenport-Hilbrand for the 3 torsion in quadratic fields. This correspondence is really what's behind that. They don't write it that way, but that's sort of what's going on behind the scenes. Okay. So maybe I'll just give one more quick example. Instead of imposing triple symmetry on the cube, one could have imposed double symmetry. So that just means that the front face and the back face are both symmetric matrices. And so what do such cubes correspond to? Well, the front face is a binary quadratic form, and the back face is a binary quadratic form. So a doubly symmetric cube you can think of as a pair of binary quadratic forms. Right? The front face is a binary quadratic form, and the back face is a binary quadratic form. Right? In terms of representation theory, right, if you have Z2 tensor Z2 tensor Z2, and you just symmetrize the last 2 factors there, you'll get Z2 tensor Sim2 Z2. So a cube, when you doubly symmetrize, you go to a pair of binary quadratic forms. And so what do the orbits of SL2Z cross SL2Z do to this particular prehomogeneous vector space? Well, if you're just symmetrizing 2 of the factors, then you have 3 ideal classes. 2 of them are now the same. Right? So if 2 of them are now the same, then the third one's determined. So really, the 2 that are same, that's the only one you need to keep around. And so the solution to this orbit problem is that if you take Z2 tensor Sim2 Z2, modulo the action of SL2Z squared, that again parameterizes just ideal classes in orders in quadratic fields. So it's interesting. Pairs of binary quadratic forms parameterize the same thing as single binary quadratic forms. So in particular, the number of orbits of discriminant D for pairs of binary quadratic forms is the same as the number of orbits of discriminant D for single binary quadratic forms. Okay, that's something that follows from this. Yeah, it doesn't, because you have 3 ideal classes. 2 of them are the same, and then the third is determined.
No, but the factor 2.
Oh, the factor 2. Oh, yeah, right. They're different kinds of binary quadratic forms. That's right. They always have a 2 in the middle. That's right. Yeah. That's right. Okay, so what was the point of all this? So the point is, so these discussions illustrate that once you have a law of composition on the space of cubes, 2 by 2 by 2 cubes, then sort of any invariant and covariant spaces, constructions that you make using the space of cubes also inherits a law of composition. Gauss composition is just one of those, but you also have a law of composition on cubes, you have a law of composition on binary cubic forms, on pairs of binary quadratic forms, and actually many other spaces that I didn't talk about that just come once you understand cubes. So the operation that I talked, so you can start with the space of cubes and you can do various representation theoretic operations. For example, symmetrization. That's the operation I was just talking about, right? You take a cube and you can talk about its triply symmetric version, and that isolates a certain kind of torsion in the class group. So symmetrization on the representation theory side, on the number theory side, it corresponds to equating the algebraic objects that were being parametrized. So for example, in the case of cubes, when you took the triply symmetric cube, then it ended up setting those 3 ideal classes all equal, right? And that's how you figured out what was being parameterized by the symmetrized version. There's also an operation called skew symmetrization, that I'll say a little bit more about, and that corresponds to taking direct sum of the algebraic objects being parametrized. There's a symplectization that takes direct sum and adds a symplectic structure. There's Hermitianization, which, so for example, if you did a Hermitianization to a cube, it would take those three ideal classes would become conjugate over a cubic extension. And so you end up parametrizing certain Galois conjugate sets. And then the most mysterious one is what I call dualization. You can take the dual representation, and arithmetically what it always turns out to correspond to is a dualization under class field theory. So I should say these are just ways, these are not theorems, these are just ways of guessing. If you start with a representation and you do some representation theoretic operation on it, like one of these, then it allows you to guess what will happen to the algebraic objects that were originally being parametrized by that object that you started with. And what's going to happen when you get the new representation, what's going to happen to those algebraic objects. So this allows one to guess what various representations parameterize. But of course, in each case, you then have to go and prove it individually for each case. Because when you do these operations on the number theoretic side, often it introduces new kinds of algebraic objects, and you need new techniques to deal with them. But the point is, once you start with the space of cubes, you can start applying all these representation theoretic operations, and you start guessing what new things are going to be parametrized by those new spaces. And by starting with a space of cubes and applying these operations, you can actually get to most of the prehomogeneous vector spaces, almost all of the prehomogeneous vector spaces, just by starting with the space of cubes. So that list of prehomogeneous vector spaces used to look like this random looking list of representations, but in fact they're all connected via these kinds of operations. And so you can think of the space of prehomogeneous vector spaces as this web that's in 5 dimensions, and you move around by these various representations, and each time you discover what's being parametrized. And that way you can build your way to some of the really big representations that have 40 or 50 dimensions by working your way up through these representation theoretic operations. So I can't really show you this web since it's 5-dimensional, but I thought here's a 2-dimensional slice. Okay. Okay, so all right, here's Gauss's law over here. Gauss composition is binary quadratic forms. Binary quadratic forms parameterize orders in quadratic fields and ideal classes. And here's the space of cubes that everything's emanating from on this page. And in fact, in the whole 5-dimensional web, they all emanate from here. So this is sort of Z2 tensor, Z2 tensor, Z2. I sort of think this is the mother of all prehomogeneous vector spaces. And then you can start applying these operations. And you can get to Gauss's law, Gauss composition of binary quadratic forms. You can get to this triply symmetric cube case, which is binary cubic forms. They parameterize orders in quadratic fields together with an order 3 ideal class. Right? Here's the space of pairs of binary quadratic forms. Remember, that's going to parameterize one ideal class and then 2 more ideal classes that are the same. And so basically, you only have to keep I2 around. Right? Okay, so this is the symmetrizing direction. Right? So we start with the space of cubes. We can doubly symmetrize. We can triply symmetrize. And what happens on the algebraic side is that you set these 3 ideal classes that we're summing to 0 are now set equal. 2 of them are set equal. All 3 are set equal. Okay, when you go down that way. Okay, what happens in skew symmetrization? That's kind of fun. So you start with Z2 tensor Z2. Let's say we skew symmetrize those 2 factors. So what happens when you take Z2 tensor Z2 and you skew symmetrize? Well, when you symmetrize, you got sim2 of Z2. When you skew symmetrize, you get wedge 2 of Z4. So there are 2 things that you're skew symmetrizing, so that's the 2. And 2 plus 2 is 4. That's why you get a 4 there. So that's that representation theoretic operation. It's a natural operation on the representation theory side. And the group SL2 cross SL2 gets replaced with SL4. That's what happens. Okay, so that's what happens on the representation theory side. And what happens on the algebraic side, what happens is that I2 and I3 get fused together and become a rank 2 module. So I2 and I3 were rank 1 modules. You take their direct sum, you get a rank 2 module. And so this space here, Z2 tensor wedge 2 Z4, parameterizes quadratic orders together with rank 2 modules. So there's a relation here, namely that the determinant of m times I should be trivial. So I is determined by m. So really, this space here is Z2 tensor wedge 2 Z4 is parameterizing rank 2 modules over orders in quadratic fields. So just like Gauss composition parameterizes rank 1 modules, this space parameterizes rank 2 modules for orders in quadratic fields. And if you fuse all three of these together, so you do a skew symmetrization of all three of these factors, then you get wedge 3 of Z6, 2 plus 2 plus 2, which is over here. And so that ends up parameterizing the rank 3 modules over orders in quadratic fields, because you fuse three things together. So anyway, you can do various combinations like this. What gets fun is when you start fusing together rings with ideals. So Z2 tensor Z2 tensor Z2 can be thought of as Z tensor Z2 tensor Z2 tensor Z2. And now you can start skew symmetrizing these kinds of factors. And if you do that, so if you fuse together these two, you'll get wedge 2 of Z3 tensor Z2 tensor Z2, right? And what happens is I1 and I2 come along for the ride, but S and I3 get fused together. So what happens when you take a quadratic order and take the direct sum with an ideal class? Turns out it has a natural quaternion algebra structure. And so this space here parameterizes quaternion algebras together with two rank 1/2 modules, in the sense, right? So the quaternion algebra has rank 4 over Z, and I1 and I2 both have rank 2. And one is a left module and one is a right module. Okay, so this parameterizes split quaternion algebras over Z. Now, if you also decide to fuse these two factors together, so this Z2 tensor Z2, you'll get a wedge 2 Z4. And these two rank 1/2 modules will glue together to become a regular rank 1 module. And so this space here, which is basically Z3 tensor wedge 2 Z4, that parameterizes rank 1 modules over quaternion algebras over Z. So this is sort of the quaternion algebra analog of Gauss composition. It parameterizes rank 1 modules over quaternion algebras. Okay, I'll mention one more thing. If you fuse all 4 of these factors together, so you get wedge 4, because they're 4 factors, Z7, 1 plus 2 plus 2 plus 2. So this is wedge 4 Z7. It turns out that's a primogenous vector space too. And what happens when you take a quadratic ring and take the direct sum with 3 ideal classes that multiply to the identity? It turns out that has the natural structure of an octonion algebra. And so this space here, wedge 4 Z7, which has dimension 35, its integer orbits parameterize octonion algebras over Z. So the space actually, there's a natural injection of this space into this one. That's right, yeah, it's a subthing, that's right, it's a subspace. Right. So this is the triply symmetric cubes that are a subspace of this. These are doubly symmetric cubes that are a subspace of this. So all these arrows mean that they're natural maps from one object into the next. So you can imagine if you started with this 35-dimensional space and said, what are the integer orbits on this thing? That would have been pretty hard, just to analyze those integer orbits. But if you work your way starting here and work your way up, then you sort of end up sweeping out all sorts of primogenous vector spaces, and you understand what objects are parameterized by those. Okay, so here's my favorite operation, which is dualization. Suppose you start with these binary cubic forms here. Remember, those binary cubic forms had 3's in the middle, right? And those corresponded to quadratic orders with order 3 ideal classes, right? 3 torsion ideal classes. Suppose one takes the dual representation. If you take the dual representation of those binary cubic forms, over Z, the dual, in a natural sense, is the space of binary cubic forms without the 3's. And what are those parameterized? Well, that was this Dillon-Faddeev correspondence. So if you take the dual, okay, so that's what allows you to go from quadratic to cubic. So, okay, how should I explain this? So if you have 3 torsion ideal classes in quadratic fields, those are naturally dual under class field theory to cubic fields. Everyone familiar with this? Maybe I'll. Right, so if you have, so say you have the rational numbers and you take a quadratic extension. If you're looking at 3 torsion ideal classes in here, the dual object to that under class field theory is unramified degree 3 extensions. So you get unramified. Right, if you're talking about 3 torsion ideal classes in here, right, then under class field theory, the index 3 things in there correspond to unramified degree 3 extensions. And one checks?
Galois.
Yeah, Galois, right. So one checks that they're, right, unramified degree 3 cyclic extensions, and one checks that if you're in that situation, then you're automatically actually Galois over Q with Galois group S3, and so this cuts out a cubic extension. Right. And so somehow, and in class field theory, the dual object to 3 torsion ideal classes in quadratic fields are cubic fields. And what this is saying is that something's true even on the level of orders here, is that if you take the object's dual under class field theory to S comma I, where I is order 3, you get a dual object, namely, so you have this dual representation, and that's going to correspond to cubic rings, as we already saw in the Dillon-Faddeev correspondence. And so this dualization allows you to go from this quadratic page to a cubic page. And so here is a set of representations. Maybe I'll put this over here. Let's see. Okay, so there's this dual line that's going very far and coming over here. Okay. And that's the cubic page. And here we have cubic rings. And then we get various spaces that map to this space of binary cubic forms that parameterize objects that have to do with cubic rings and cubic fields. So in particular, just like Z2 tensor Z2 tensor Z2, the space of cubes was sort of the master of this quadratic page, Z2 tensor Z2 tensor Z2 gets replaced by Z2 tensor Z3 tensor Z3, and that's sort of the master of the cubic page, and everything comes from there. And this space parameterizes cubic rings together with 2 ideal classes that multiply to the trivial class. So the way you can think of this as a pair of 3 by 3 matrices, right? Z2 tensor Z3 tensor Z3 is a pair of 3 by 3 matrices. And what do you do when you have a pair of 3 by 3 matrices, right? A and B. You multiply A by an indeterminate and B by an indeterminate, add them, and take the determinant. And when you do that, you get a cubic form, a binary cubic form. And that's the cubic ring that corresponds to the binary cubic form. So that's how you get the cubic ring. But this extra information here corresponds to 2 extra ideal classes, which I didn't tell you how to make, but you can make them. And this, in fact, is an exact parameterization. And so, of course, I1 and I2 multiply to the identity here. So basically, everything's determined by I1. So this space really just parameterizes cubic rings together with an ideal class. So this space here is the cubic analog of Gauss composition. Okay, it parameterizes ideal classes in orders and cubic fields. And then again, you can symmetrize to extract order 2 ideal classes in cubic fields. You can skew symmetrize to get rank 2 modules over orders in cubic fields. You can do something mysterious here, and I don't know what happens. And finally, you can skew symmetrize all 3 of these together. So what happens when you take a cubic ring together with 2 ideal classes that multiply to the identity, and you fuse them together, you take the direct sum. And that turns out to have a natural structure of a rank 9 division algebra over Z. And you have to define what that means, but you get a rank 9 division algebra over Z when you take these 3 objects together and you fuse them together. So it turns out Wedge 3Z8, this is also a prehomogeneous vector space, 56 dimensional, and it parameterizes rank 9 division algebras over Z. And again, if you just started with the space, it'd be really hard to understand what the integer orbits mean. But here, you figure out that the integer orbits, it comes with the definition that the orbits correspond to certain rank 9 algebras over Z that have a certain structure, division algebra-like structure. Okay, now how do we go to even higher number fields? I should mention all these spaces that I'm talking about, they're prehomogeneous vector spaces. They also have an intimate connection with the exceptional Lie algebras. So and if you're interested in knowing about that, I'm happy to talk about it afterwards. Yeah.
So acting up there at the top of this picture?
Oh, sorry. So SL8 is acting on wedge 3Z8. SL3 cross SL5. Yeah, it's basically just a product of SLs. You look at the exponents of the Z's, and those are the SLs that are acting. So these representations, even on the quadratic page, they all come from the exceptional Lie groups in a very special way. It's a bit mysterious, but I'm happy to tell you more about that if you're interested. But again, you can do a dualization procedure here. So you always go to the bottom right corner, and you think, OK, what happens if you dualize this object? OK, so this is order 2 ideal classes in cubic fields. If you make the analogous picture for order 2 ideal classes in cubic fields, it turns out you get quartic fields. You can make it if you want. So you start with, so say you start with a cubic field, and then you look at order 2 ideal classes in here. The dual object is unramified quadratic extensions. So it's unramified. And now if you take the Galois closure, turns out that that's, if this was non-cyclic, then this will be an S4 extension. And so it cuts out a quartic field. And so the dual object to order 2 ideal classes in here are quartic fields under class field theory. And this is a ring. This is a realization of that on the level of rings. So what happens is you look at these pairs of symmetric 3 by 3 matrices, right? And if you dualize the representation, these matrices had 2s. Had 2s in the cross terms. The dual won't have 2s in the cross terms. And so you get this representation, which is pairs of conics, as Henri was talking about today. So pairs of conics in the plane, they cut out 4 points. And on the level of the integer orbits on this representation turn out to parameterize basically quartic rings, together with some additional information on the resolvent, the cubic resolvent ring. So that parameterizes quartic rings. And so that's the quartic page. It's not very big. Of course, these are slices. There are other things that are going on, but I just want to mention there's a natural line that goes through that z tilde there, and binary cubic forms, and then this space, and ends up at this space that corresponds to quintics. So this space, z4 tensor wedge 2 z5, quadruples of alternating 2 forms in 5 variables. The integer orbits on this prehomogeneous vector space turn out to correspond to quintic rings, okay, basically orders in quintic fields, together with some information about a sextic resolvent ring. So these are exact correspondences of the orbits with these algebraic objects. So these are sort of algebraic parameterizations by prehomogeneous vector spaces. And what we found is that by these representation theoretic operations, we could sweep out all prehomogeneous vector spaces, and they all parameterized, except for the couple of question marks that I had. They all seem to parameterize, and probably those do too. I think some of these correspond to algebraic objects that I've never seen definitions of, and so I don't know what to call them. And that question mark was one of them. When you're doing these operations, it really tells you what the algebraic objects you are getting. And amazingly, almost all of them had names previously. And it makes me believe that all these algebraic objects that were been defined. You sometimes wonder, is that a natural algebraic object? I always wondered, octonions, is that a natural algebraic object? Well, it sort of comes out from these operations on prehomogeneous vector spaces. And I always find it amazing when I just find an algebraic object that already has been named. And then a couple that haven't been named. So I think maybe those are new natural algebraic objects that should be studied, but I don't know what they mean. OK, so the situation is that there are all these prehomogeneous vector spaces, and we now basically understand what the integer orbits on each of these prehomogeneous vector spaces parameterize. And they all amazingly parameterize very interesting arithmetic objects. Unless you don't think octonions are interesting arithmetic objects, I don't know. But they all parameterize some kind of arithmetic objects, and some of them are of a lot of interest to number theorists, and some are of interest to fewer number theorists. But these things really convinced me. For example, octonions I really got into because of this way of building from ideal classes and quadratic fields to octonions. It really gives an arithmetic interpretation to octonian algebras, for example. So prehomogeneous vector spaces are not a random list of representations, but they're in fact a web that are connected in a very natural way, arithmetically and representation theoretically. OK, so I want to mention just a few applications, and then I'll get more into the arithmetic statistics kinds of applications tomorrow, as well as other representations. I was just talking about prehomogeneous today as background. So first of all, there are computational applications, as Henri already mentioned. So there are work of Shanks that use binary quadratic forms to do calculations with ideal classes and quadratic fields, and there's work of Belabas in doing calculations with cubic fields using binary cubic forms. I think Anamura had started this implementation of the quartic case, and so on. So there's those applications. Once you have such parameterizations, like binary quadratics and binary cubics have had the best ways of computing with ideal classes and quadratic fields and cubic fields, we now have a whole host of representations, and those should give efficient ways of computing with all these algebraic objects. Okay, the second application is to theory of pre-homogeneous vector spaces. So there's a whole theory of zeta functions of pre-homogeneous vector spaces due to Sato and Shintani, and developed by Daskovsky and Wright and Yuki, and now by Taniguchi and Thorne, as you'll hear more about this week. So most of this works have been for binary cubic forms, because that was sort of the biggest pre-homogeneous vector space at the time that had this kind of arithmetic interpretation. But now we have lots of pre-homogeneous vector spaces whose orbits have interpretations, and so their zeta functions would be of interest to study for that reason. There's also a connection with modular forms on exceptional groups that was developed by Gann, Gross, and Savin. They showed that if you look at modular forms on G2, then Fourier coefficients for such modular forms are naturally indexed by binary cubic forms and thus by cubic rings. And now these later works by Lucianovic and Weissman and Volpato show that a lot of these other pre-homogeneous vector spaces, their orbits come up as naturally as the Fourier coefficients for modular forms on other exceptional groups. And now that we know what those orbits mean, that allows you to study those kinds of modular forms from that perspective in terms of the Fourier expansions. There are also nice applications to non-commutative algebras, because now we have all these parameterizations for various non-commutative algebras, and so one can study structures of non-commutative algebras by studying orbits of these representations. There's a nice work of Krudilevich to understand some of the exceptional Jordan algebras through these representations. Okay, so what I'll start talking about tomorrow a little bit is how one can use these kinds of parameterizations to understand sort of theorems in arithmetic statistics. How many such algebraic objects are there that have given invariance? Well, now that we have an explicit parameterization of a lot of these arithmetic objects, for example, orders and quartic fields, we can try to ask questions like how many orders and quartic fields are there that have bounded discriminant, or that have certain other invariant properties, or if you count them in different ways, what happens? These can start to be addressed once you have these parameterizations. And so I'll talk more about that tomorrow. And the other thing I'll start talking about is non-prehomogeneous representations. And those are where you start having connections with arithmetic objects that have more than one invariant. For example, algebraic curves and Jacobians of algebraic curves and other such objects that have moduli. So, okay, so I'll stop there. Okay, thanks.